What volume of 0.250 molar HNO3? So your concentration of HNO3, see these brackets? How I drew that? That is a common symbology for molar. The brackets mean molar concentrations. Okay, the molar concentration given is a 0.250 molar aqueous solution. And we want to react that with 44.8 milliliters of a 0.15 molar sodium carbonate solution, like that. Okay, well, one of the exercises in chemistry is being able to write the metathesis reaction from the problem. So here we have a nitric acid right here, plus the sodium carbonate right here as a double replacement going to sodium nitrate, plus the carbonic acid. And of course that goes to CO2 and water and breaks down. So we need to balance this, and we're going to need a couple of sodiums there, and that's already balanced. And I got a couple of nitrates, so I need a couple of those, and it looks like everything else is pretty much balanced in there. Two nitrates, two sodiums, a carbonate, and there's your carbonates breaking out. So we have a 2-to-1 reaction ratio. Yeah? Now the problem that you're looking at says, how does one reactant interact with the other reactant? So I really don't need this part of the equation. So what I'm going to do is I'm going to say 2HNO3 plus Na2CO3 goes to whatever. Okay, and then I'll come down here and start putting in my data in here. So it says we have what volume of nitric acid, so volume of HNO3, and we have a 0.25 molar solution here. And then we have the, I'm going to move that over so it looks a little better, plus sodium carbonate, and whatever, like that. And we over here we have 44.8 milliliters of 0.15 molar of the sodium carbonate. So that's our rough data that we have. Now, what I tell people in working with solution phase or any kind of reaction problem, convert to moles, and then solve the problem in terms of moles. And if they want something else, you convert it back to whatever they're looking for. Now, in this problem, you have a 2-to-1 ratio. And moles, if you recall, is molarity times volume. Molarity times volume, and we'll put it in liters for right now. Okay? So I have a certain number of moles of HNO3 and a certain number of moles of sodium carbonate here. So what I want to do is I want to write me an equation using this expression in terms of solution expression, molarity and volume. And I want to set these two equal. Well, if this is 2 as a coefficient of HNO3, then this one is doing whatever it does twice as much as the sodium carbonate. But I can make them equal if I move that 2 over to the carbonate side. I'll show you. Molarity times volume, expressed in liters if you want to do that, HNO3 is moles of the carbonate, right? That's what I said. Here it is right here. Moles of nitric acid. And we want to set that equal to moles of the sodium carbonate solution, like that. Well, that's not true in the way I've written it in this context, because we have different numbers. However, I can swap the coefficients. So I can take the coefficient off the equation and put it in the front of this sodium carbonate expression, and the coefficient in front of the sodium carbonate, put it in front of the HNO3 expression. Now I have one I can work with and solve for that mystery volume is what we're looking for right here and here. So the volume, you can do it in liters or milliliters now, and liters is 2 times molarity times volume of whatever that sodium carbonate data is, divided by the molarity of the HNO3. And so if you did it, if you expressed everything in liters, but in this case, we can leave it in milliliters because we have the same units on both sides of the equation, and that's the exception. And we'll do one that's not an exception. You have to use liters. But anyway, we can put milliliters in here and do this in milliliters if we want to. And so let me move that up here. Okay, so that would be 2. All right, the molarity of the sodium carbonate is 0.15 moles per liter. And we have milliliters, 44.8 milliliters here. And that's divided by moles per liter of the nitric acid. And so that will cancel out very neatly. That's what I'm trying to tell you. Sometimes you can get away with using milliliters and make it really simple in the process. And so that's 53.76 is what I got. The 0.25 molar HNO3. Okay, now I know that it's kind of fragmented, but I'm going to do this over and over and over today as we go through this, and hopefully things will start falling in place. That number 2 problem here is you're given calcium hydroxide, and it's going to react with sodium carbonate, and it's going to be a double replacement again. See, you're going to get sodium hydroxide, and you're going to get some calcium carbonate out of it. Okay, whatever the products are, who cares? I mean, because we're going to work primarily with the reactant side, but you still have to balance this thing and make sure you have enough of whatever you're involved with. So we have 2 sodium. I got hydroxides. I got a couple of hydroxides, calcium and calcium carbonate. So this is a 1-to-1 on the reactant side. Now, if we were asked to predict how much sodium hydroxide, based on the limiting reagent on the reactant side, it'd be a 1-to-2 reaction. And we'll cover that in a minute. So bear with me on this. Okay, so what are we given in here? We got 49 milliliters calcium hydroxide, so 49.8 milliliters of 0.15 molar of the calcium hydroxide. I can get rid of that. Make it easy for you. What volume, and we'll do that in milliliters again, because both sides are the same, 0.35 molar here. Now you set those equal. You don't need to swap coefficients here and just solve for whatever the volume is, because molarity times volume is moles. And so we have 49.8 milliliters of 0.15 molar is now equal to the volume in milliliters of 0.35 molar of the sodium carbonate. Solving for the volume in milliliters of the sodium carbonate, put that in here, is equal to 49.8 milliliters, 0.15 molar, and 0.35 molar. Molarities drop out, and looks like we're looking at 21 milliliters. 21 milliliters of the sodium carbonate solution. So you want to relate the reactants or whatever the yielding product in terms of molarity times volume, because that's moles, moles, moles as we go through this. Okay, let's look at another one. Okay, so and as number 3, what are we reacting? Start there. Okay, so we got H2SO4 reacting with sodium hydroxide. And this is going to sodium sulfate and water, like that. So we want to balance this, so I've got to have a 2 here. You know. And so I got 2 sodiums, 2 hydroxides, 2, 4. I need a 2 here. And I think we got enough. Yeah, we do. Okay, so this is a 1 to 2 reaction ratio now, yes? So if I want to equate those in terms of solution data or moles and moles, I can say, well, moles of H2SO4 is equal to moles of sodium hydroxide. But to say that, I have to take and put a 2 in front of whatever moles of sulfuric acid I have, because you're going to have twice as much for the react with. Well, you have to have twice as much sodium hydroxide, but you have half as much over here. So to make them equal, you have to double that sulfuric acid, like that. So anyway, well, what's moles? It's molarity times volume. Well, over here, our data is given in molarity and volume, so I can go ahead and molarity and volume. Now, I need to stay in liters in this one. And this is going to be equal to moles of the sodium hydroxide. Well, it didn't give us in moles. They gave us 8.20 grams of sodium hydroxide. Well, I need to convert that to moles, and then I can solve for that volume that I need. Okay? And so this is 23, 33, 40 grams per mole. And so see, that comes out. I didn't work that out that tightly. Molarity here is 2, and the molarity of our H2SO4 solution 0.15 is 0.15 molar. And put my units in. Volume in liters is now 8.20 over 4 grams. That's moles here. So when you work this out, you're going to wind up in liters, because you remember molarity is moles per liter. And then when you work, put all the units in, so the volume in liters now is 8.20 divided by 40, and then that's divided by, well, go to 0.15, like that. And that will give us that. I got 0.683 liters, or 683 milliliters. You want to punch it to calculate, like that. Now, I didn't do anything different here, except, I couldn't use a molarity times volume on this product side over here. On the right side of the expression, because everything was given in mass and grams and terms, but I can equate it to solution data, because molarity times volume is moles. So it's really still a mole problem. See that? Okay? Check mark that. One size mole. Everything stays in moles, and then you substitute in what you need to convert to whatever you're asking for. We'll work some. Like a solution of hydrogen peroxide is titrated with a solution of potassium permanganate. I can read it with you here. And the balance equation is this nasty looking thing here. So it requires 51.7 milliliters of the permanganate, 0.145 molar, to titrate 20 grams of the solution of hydrogen peroxide. Now you've got a 20-gram solution. Now we want to know the percentage of H2O2 in the solution. What's the percentage? What do we need here? We need the grams of H2O2 and divide that by 20 times 100, right? Everybody look at it. So it's asking for the percentage of hydrogen peroxide. So I'm just out of this mass of data and stuff, I've got to get the mass of hydrogen peroxide that's associated with that titration, with the reaction. And the only two in there that really are of interest to me are the H2O2. So I can get moles of H2O2. I can convert moles to grams, can I? If I can get moles there. Moles, moles, moles. And over here, however many moles I have over here, I can relate to the H2O2. So I can use my data to get the moles of KMnO4 and relate that over here to the moles of H2O2. So all the rest of this stuff in here, I can ignore because I'm only needing two of them that are involved in the titration. So let's look at this. Okay, so I'm just going to take the H2O2 and react that with the 2KMnO4. And then it goes plus whatever else we've got in there. 4 more. Okay, it says it requires 51.7 milliliters of the 0.145 molar potassium permanganate. So I have 51.7 milliliters of a 0.145 molar solution that I use. Okay, and you know what a titration is if you've ever seen them. This is a burette and added down into another solution like that. So we may say the KMnO4 is up here. Say something like that, and then you might have your H2O2 down here somewhere, and you know, and you're titrating that 20 grams. This is 20-gram solution down here. Okay, and you're just trying to find out how much H2O2 is in that beaker. Okay, so I'm going to cover this. We'll do more of that in the lab, hands on. Okay, so I can use this to relate over here to my moles of H2O2. Okay, I want to set that equal. I want moles of H2O2 equal to the moles of the KMnO4. Every problem I started, I balanced the thing. Then I took moles of one reagent equals the moles of the other. And then I made the statement, I said, is this true or not true? Is this true or not? Can I write that? Is that true? Come on, guys, let's get the brains going. Is that true based on this equation? No. I have a 5-2 ratio. Now, if it was 1-to-1, yeah, I could write that and start plugging numbers in, right? Okay. But to make that real, I'm going to have to bring my coefficient for the KMnO4 over to the H2O2 moles, and then I'll take 5 and put it over here. That's true. Okay? Now, this is solution data right here. Well, how am I going to get moles out of that solution data? Remember what I told you? Moles is equal to what? Molarity times volume. Okay, so now I have 5 times the molarity times the volume, and it's going to have to stay in liters, and this will be the KMnO4 side. Now, whatever moles we get out of this thing, whatever's over here, whatever numbers we get, relates to that moles of H2O2. And that's what we need, the moles of H2O2. So I have 2 onto moles of H2O2. Now, that's what it is. Okay? So I'm going to solve that for moles of H2O2, and that's 5 times molarity times volume in liters of the KMnO4 stuff divided by 2. Y'all keeping up with me? All I'm doing is math now. See, I won't try to teach you take the equation and all the data and pick out the 2 that you need to work with, you know, and set them equal. Moles of reagent 1 equals moles of reagent 2. Swap the coefficients, and then start plugging in what you need. You follow me? Okay, good. So now I start plugging in what I need, and so that's 5. Molarity is 0.145 molar up here, and I need to stay in liters, so I need to move that decimal over 0.517 liters, and that's KMnO4, but that's all right. divided by 2. Now this is moles per liter, so when I cancel all this out, I'm going to left with moles of H2O2. That's what it's going to give me. You know that one? And punching all of that in, I got 0.019 mole of H2O2 is what that's telling me. Because see, that's what moles of H2O2 related to the solution data. The solution data's got to be converted to moles, and that's what I did. And set those equal. I swapped coefficients, plugged in the data, and there's my moles of H2O2. Now, in order to calculate a percentage, I need to convert moles to grams. So we need to multiply it times the formula weight. There's 32, 34. That's 34 grams per mole. And so the grams turns out to be 0.637 grams of H2O2. Like that. So now I can calculate the percent of H2O2 is equal to part over total. Well, the total is the solution, and that was 20 grams of solution. And we have 0.637 grams in the solution, grams of H2O2. And of course, multiply times 100, I got a 3.19% solution. Now you're going to have to dig through one of these. I'm not going to give you a lot of them, but you will have to kind of untangle. And it all starts with identifying which two reagents are really reacting in here to give you the appropriate outcome of the problem. Okay, we got another one in here. All right, let's think about the problem. All right, this is number 5. A sample weight is 3.33 grams ore. So we need to find what? The grams of iron that's in that ore sample. Yes? Okay, so we look at our problem and we say, well, what's going on? Well, we've converted to iron sulfate, okay, by putting it into, this is what it says right here. It says we're making iron 2 sulfate. And this solution is titrated with, you can put this in, 1,5 molar potassium chromate, dichromate. Right there. Okay, and we're going to use 43.7 milliliters of the chromate to reach the end point. Well, in this reaction, it really balances it. It shows you down there. You have 6 iron sulfates plus potassium chromate, K2Cr2O7, plus all the rest of the stuff. Well, those are the only 2 I really need, but that's all the data we've got. You don't need to go worry about all the other stuff unless somebody's testing you to balance the oxidation reduction. We didn't do that. Iron sulfate, iron is a salt, metal, and a non-metal component, always ionizes. How much? 100%. Salt ionizes 100%. So really, this is 6 moles of iron 2, plus whatever 6 moles of sulfate, plus actually is reacting with a Cr2O7, 2 minus. So it's a 6-to-1 reaction ratio. Is what we're looking at. Now, what did I tell you to do when you use these kind of things? When you can find the 2 that you want. Molarity times volume equals molarity times volume, didn't it? Okay, everybody kind of catching that drill? Okay, so these are 2, so I want molarity times volume of the iron part of this equal to the molarity times volume of the Cr2O7. Actually, this would be moles over here. Moles and moles. Let me back that up before we start throwing those in. We want moles over here of the iron sample, and then we have moles of the chromate, 2 minus, like that. Then what do? Can I make this statement? That's correct, no. So what I need to do is put a 6 right here and a 1 over here. Now I'm in position to start substituting solution data. Okay, because moles is equal to what? Molarity times volume, right? Okay, what have I got up here as the solution data? Well, that's chromate. Yeah. So over here, I'm going to have 6 on the molarity times volume expressed in liters of the K2Cr2O7 chromate solution. I haven't done anything different than I did in the previous problem. And then over here, if I get the moles of iron, can I convert it to grams? Well, 58 grams per mole. Multiply the formula weight times the moles I get out of this. So, put this up here. And so the moles of iron titrated, this is what you have, and you have 6. The molarity was a 0.15 molar chromate, and you use 43.7 mils. And since we don't have milliliters on both sides, we have to use liters here, 0.437 liters, and that's divided by, well, 1. Okay, so that makes life real easy for us. So I got 0.00675 mole, 0.00675 mole of the iron titrated. Now, that is equal to, and that gives us, I'll move that up just a touch, 0.00675 mole times 58 grams per mole, and what did I get out of that? 0.378 grams of iron. See, that's what the titration gave us. We went to moles, and then our sample weight's 3.3 grams. So now I can get the percentage of iron. 0.378 grams of iron and 33.3 grams of the ore times 100%. See what I got 11.35% and that 5%. Now these two problems are very, very common type problems in analytical laboratories, where you have some oxidation reduction reaction, you're titrating one against the other, and you have to calculate at whatever percentage and identifying that concentration. Fundamentally, and I'm going to expand this a little bit on this problem. An acid reacts with a base and always produces a salt and a weak electrolyte, or weak acid over here. And water is the most common, okay? And in this particular one, we have HNO3, an aqueous, plus sodium hydroxide, aqueous. And I set it up so it'll be a 1-to-1. Here's your sodium nitrate and H2O, and that's your driving force, blah, blah, blah. Okay, now, what I'm interested in is showing you how you focus in an acid-base reaction, focus only on the reactive side. And so what do you see to begin with? The moles, this is a 1-to-1 reaction ratio, and I set it up just like that. If it wasn't, it was a 2-to-1 like sulfuric acid or something, and sodium hydroxide, then you'd have to swap coefficients, but this is a 1-to-1. And just turns out moles of HNO3 neutralized is equal to the moles of sodium hydroxide used in the titration. Now, when I can use that, okay, well, actually, I didn't want to put an equal sign in there. I really didn't. So this, put a plus in here. Moles of this one plus moles of that one. Sorry, got a point to make. Now, I can go molarity times volume of the HNO3, and you want to keep this in liters, plus molarity times volume in liters of the sodium hydroxide. Now, if you look, you got moles, 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 moles. Now, put in your solution data. And so what we're mixing, 35 milliliters of 0.111 molar HNO3. So we have 35 milliliters of 0.111 molar plus 33 milliliters of the 0.086 molar. See, moles, moles again. Moles, moles. Okay? Now, in this, I need to convert these to moles. Well, molarity times volume in liters. So what I'm going to do is I'm going to take this. Now, this is what I'm talking about protocol. Convert this to liters. 0.035 liters times 0.111 molar is moles of the HNO3. You're reacting with 0.033 times 0.086 mole of the sodium hydroxide. Right there. So you're going to get a number, which is your mole. Now study that for a second. So here we have 1-to-1 reaction ratio. So moles and moles. Now one of them's going to be the limiting reagent. What's going to happen? Okay, so this comes out to be, by my calculator, 0.0039 mole HNO3 reacting with mixed with, actually, 0.00284 mole of the sodium hydroxide. So down here, see, I took the difference in those two because the sodium hydroxide is gone, and I used up only that much of the nitric acid, and so this leaves me with an excess of 0.00106 mole of HNO3 excess acid. So the final solution in the mix is going to be acidic. It just says this is from your stoichiometry worksheet. Big one right here. Okay, so all right, number one in here. Now, what I want you to pay attention to is, are you beginning to see the flow of how to deal with this? We start with moles and we expand it out to the molarity times volume issue. Okay, so what we have here in this one, how many grams of aluminum are required to react with 35 milliliters of the 2 molar hydrochloric acid? Well, that's the same kind of problem, except we're talking about grams now. On one side is what we're looking for, a product item. So here's our HCl, and we want to react that with aluminum, and that's going to aluminum chloride and molecular hydrogen, like that. So it's making you balance the equation now. So I have 3 chlorides here. I'm going to bring that up to a 3, but then we'll need a 3 over here, and I'm going to have to go to a 6. 2 to 3 is 6. So if I've got 6 chlorides, I'm going to have a 2 there, and finally a 2 right there. Okay, now this is Chem 1 stuff, guys. You learn to balance equations if you're struggling with it. Okay, so what do we have here? The question in here is how many grams of aluminum are needed? Okay, and based on 35 milliliters of 2 molar hydrochloric acid. So we got 35 milliliters of 2 molar acid right there. Now, what's the solution of a problem? Moles to moles, right? We got our 2 reagents that we're working with, so we want to equate those 2. So I got moles of HCl to equal moles of the aluminum now. We want to focus on. Well, who's what in here? Well, how do I take this data and convert it into moles? Molarity times volume, right? Everybody starting to see the train of thought? So molarity times volume expressed in liters for the HCl is equal to, well, this is going to go to grams, so we're just interested in moles over here. Moles of aluminum, because once we get moles of aluminum times this formula weight gives us a what? A mass number. What we're ultimately looking for. Let's see what we got. So from the data given, moles of HCl, that would be 2 molar times 0.035 liters is going to give me the moles of aluminum. And so 0.7. Oh, wait a minute. Somebody's going to pinch my head off here. My bad. We forgot to go the coefficient route. 2 and 6. 2 and 6. My bad. Okay. Should be 2 and 6 right there. Carried away. Now, let's put the data in. So we have 2 times HCl will be 30. We've got to stay in liters now, 0.035 liters. And we have 2 molar. And this is 6 aluminum. And it'll come out moles of aluminum. And whatever. Put that over here like that. Like that. And solve for moles of aluminum. 2 times 0.035 liters times 2 molar divided by 6. And so this will work out in moles of aluminum. See, moles per liter, and then we wind up, remember that's moles per liter, cancel the liters out. So we're left with moles, and the outcome is, according to my notes, 0.0233 mole of aluminum are needed in that reaction. And so grams of aluminum is 0.0233. 6 goes up there. Mole times 27 grams mole, and I get 0.63 gram aluminum used in the reaction. Sorry about the 2-6 moves. So I haven't done anything different. I'm just trying to get you acclimated now to using the connecting moles to solution data. Okay, you're given 45 milliliters of 1.5 molar silver nitrate is added to KCl. How many grams of silver chloride can be formed? So this is, they're asking us what the outcome of the yield is in the product. So here's our equation. We've got silver nitrate, and that's reacting with a KCl solution, and that's going to silver chloride, which will G chloride, potassium nitrate. And so to balance this is a 1-to-1, so that's correct. So I got 1 silver, nitrate. So it's already a 1-to-1 all. I don't have to do any more to it. Everybody okay on that? Everybody see a 1-to-1? Any questions? All right. Now start plugging in the data. We're using 45 milliliters of 1.5 nitrate, okay, solution, and we're assuming an excess. See, it didn't mention anything about the KCl, so it's added to a KCl is all it said. It didn't give you any quantity. So when it presents it like that, you assume an excess. And so the question is, how many grams of silver chloride is generated? Well, we first want to calculate moles and then multiply by formula weight, right? So I need moles of this and moles of that. This is a 1-to-1. So if I can get the moles of silver nitrate, excuse me, then I can get the moles of silver chloride because it's a 1-to-1 reaction ratio. Everybody okay on that? Okay, so to get moles of this, so this would give me 0.045 times 1.5 mole of the AgNO3 is equal to also the moles of silver chloride, because the reaction says it's 1-to-1. And so punching that into your calculator, I get 0.675. Which tells me I've got 0.0675 mole of silver chloride yield. Which also gives me that much. Well, 0.0675 mole of silver chloride equals 0.067 identity mole, and that's 142 grams per mole. And so moles drop out, left with grams of silver chloride, and I got 0.945 gram of the silver chloride. So there's your yield. As a matter of fact, that is referred to as a theoretical yield. Just to review a Chem 1 note here, theoretical means that it is calculated from the equation. Now, no reaction is absolutely perfect yield. Okay, I think you appreciate that. Let's assume you go to the lab and your yield, lab yield, is, say, 0.812 grams instead of the expected 9.945. This is called the lab yield, or practical yield. What's the percent yield? Well, to review this, percent yield is always the actual divided by theoretical times 100. That's all it is. Actual, which is lab yield, over theoretical, times 100%. And so, plugging that into here, we have 0.812 over 0.945 times 100%. And for review purposes, about 85.9%. So this is kind of not in the problem, but I made that up for your benefit, because you will have to deal with yield at some point in your lifetime. How many liters of a 0.75 molar calcium nitrate solution would be required to react with 148 grams of sodium carbonate? Start with the reaction like we always have, and let's balance that. So we have, this is number 4 in that sheet, calcium nitrate reacting with sodium carbonate. I tell you what, goes to calcium carbonate and sodium nitrate. Okay. Guys, correct your notes on this. I just punched it in the calculator. Should be 9.58 grams, and change this to 8.12. Give you an 84% yield. The silver chloride should have come out 9.58 instead of whatever I had. Then I changed the problem on theoretical yield and percent yield to 8.12 and 84%. So please make those corrections. Okay, we left off on number 4 with calcium nitrate, sodium carbonate. I went ahead and filled in some data from the problem. And so we identified the two reagents we need, which is calcium nitrate and your sodium carbonate. So we want a mole-mole relationship between those, and then plug in the data into that mole-mole relationship and work from there. So, and balancing the equation is already balanced in the 1-to-1. So being a 1-to-1 reaction ratio, so the moles of one only equal the moles of whatever the other one is. So we'll start out there and talk about in terms of moles of calcium nitrate, right there, is equal to the moles of sodium carbonate, right there. And so we want to know what volume of the 0.75. Well, we know molarity times volume expressed in liters is also moles, so we'll make that in the calcium nitrate, like that. And then we had 148 grams of the sodium carbonate, so we have equal to 148 grams of the moles. We'll just put moles sodium carbonate. Now, putting in our data, we have the molarity 0.75 molar times the volume. Now, when we finish our calculation, we have liters, okay? And moles of that would be 148 grams divided by the formula weight, sodium carbonate. And I got 106 grams per mole. And that works out to 1.4 mole of the sodium carbonate. Okay, so solving for volume in liters is 1.4 mole divided by 0.75 mole per liter. Because molarity is moles per liter, moles drop out, and so the answer comes out in liters. If I punched it in correctly, I got 1.9 liters of the calcium nitrate solution. So hopefully you're getting the gist of the relationships. You start out with the moles and moles, and then you substitute your data in there. Okay, I want to go to number 6. I'm trying to give you one of each type. All right, so number 6 in here and see what it says. Okay. How many milliliters of a 0.1 molar lead nitrate are required to react with 75 milliliters of 0.2 molar sodium iodide? So all of this is solution data. Okay, so we want a mole-mole relationship, but then we substitute molarity times volume, swap coefficients, what have you like that. So let's start with the equation here. Lead nitrate sodium iodide, and that will go to lead iodide, which will be a driving force, and then sodium nitrate, which is site. Okay. I've got a 2 goes right there, and a 2 would go right there. Okay, and then we start putting in our data, and the question is how many milliliters of the 0.10 molar lead nitrate, and we'll react with 75 milliliters of the 0.20 molar sodium iodide in this case. Well, we have a 2-to-1 reaction ratio, so we could say moles of lead nitrate equals moles of sodium iodide. Swap coefficients, bring the 2 over here and a 1 right there. Okay, so that sets up that relationship, the mole-mole relationship. Well, we have molarity times volume is moles, so we can go 2 times molarity times volume expressed. We'll leave it in milliliters this time because both sides will be the same. Volume in milliliters of the lead nitrate is equal to 1 onto molarity times volume in milliliters of the sodium iodide solution, like that. So we're starting to focus on the objective of the problem now. So we either put in the data or solve this one. So the lead nitrate, so it's 2 onto 0.10 molar volume in milliliters of the lead nitrate right there. And that's equal to 1 onto the molarity 0.20 molar times 75 milliliters. And of course that is the sodium iodide. Solving for the volume milliliters of the lead nitrate, 1 times 0.20 molar times 75 mils divided by 2 times 0.10 molar. Molarities drop out, we're left in milliliters. So hopefully you're starting to get a little better feel for the idea of working with the solution reactions. And I got, if I didn't miss it, 66.7 mils. No, that's the wrong one. 75 milliliters. 75 milliliters of PbNO3 solution. Okay. Last one in this set, when you work through, is number 8. Starting with the reaction, we'll have HCl plus strontium hydroxide goes to strontium chloride and plus water and that one. So that balances 2 and a 2 right there. Okay. Now, in the data that's given, we have 525 milliliters of a 0.80 molar hydrochloric acid, and then we're mixing that with 315 milliliters of an unknown molarity in the strontium hydroxide is what we're looking for. So we start out with a moles of HCl equals moles of strontium hydroxide, just like we've been doing. So is it a 1-to-1? No, it's not. So we have to double this one and 1 times this one. Then we can plug in the molarity times volume expression. And so 1 times molarity times volume, this will be the HCl side. This will be 2 times molarity times volume of the strontium hydroxide side. Plugging in the appropriate data, we have 0.80 molar times 525 milliliters. We can leave it milliliters since both sides have the same units. And then 2 times the molarity, well, the volume is here 315 milliliters, and then finally the molarity of the strontium hydroxide is what we're solving for. so now the molarity of the strontium hydroxide solution is 1 times 0.80 molar times 525 milliliters, and divided by 2 times 315 mils. It drops out, and we're left with molarity. And so, okay. So that gives you a cross-section of several types of solution phase reaction problems that you can work and working in this area. So if you have this, I think that page 15 in that handout that I gave you, and has a number, and it's got the equations already balanced for you, so that should save us a lot of time here. Okay, so here we are with this one, and we got 150 mils of silver nitrate, 0.5 molar, and 100 milliliters of chromate. So 100 mils of 0.40 molar in the chromate. Now, one of them may be a limiting reagent in here. Okay, how do you determine if it's a limiting reagent? You calculate moles and then divide by the coefficient. Smaller a number is the limiting reagent, and you work the problem from the limiting reagent. Okay, so what I want to do is convert this to liters and get moles out of it. Liters right here, and then times 0.5 molar, and that gives me the moles of 6.15. I'm sorry? I'm just getting the moles first, and then we'll do mole. Okay, well, we can do it that way. Okay, we can set it up that way if you want to. We take moles of silver nitrate equal moles of the K2CrO4. I was just going to figure out what moles that anyway. So it's a 2 to 1 ratio. Now, we still need moles out of this. So it'd be 1 times 0.150 moles, liters, times 0.50 molar. That gives me my moles of the silver nitrate. So I got molarity times volume in liters. And this equal to 2 times the moles. See, we've got to find out the moles. We don't need to equate them yet. We can't equate them. That's right. You can't equate this in this case, because see, you have to determine which one of these limiting reagents. That threw me for a second there. So this is not correct. You need to take that out, and we got to do moles first. So this is 0.15 times 0.5 mole over here, and that's equal to also 0.1 times 0.4 mole of the chromate. And so that's 0.04 mole and 5. 0.075 mole, like this. So how much are you going to use? One against the other. So we divide by 2 here, divide this one by 1, and so that's divided by 2, 0.0375, 0.0375, and this one divided by 1 gives you 0.040. Well, this is your limiting reagent right here. Remember what I showed you last time. You convert to moles and then divide by the respective coefficient. Now, so everything revolves around this one. So how much of this chromate are you going to use? Well, you have 2 to 0.075. You have to go back up to this one to when you work your problem is equal to 1 to x. And so what is x? So we have 2x is equal to 0.075, and x is equal to 0.75 over 2. 0.0375 mole of the chromate. So 4. 0.0375 mole of the chromate used. Okay, so you didn't use all of it. So we have 0.04, but we only used 0.0375. So that's why you can't equate them. You can't say one equals the other or one's twice as much as the other in this case. Only if the problem specifies that everything's completely reacted out. Okay, well, the problem wants to know what the silver chromate is in the yield over here. So once we have the moles of that, it's half. It's a 2-to-1 ratio in that case. So if we are using 0.0375 mole of the silver nitrate, then how many moles of the silver chromate? Well, half of that, 0.0375 mole of the silver chromate. Probably off the board by now. I'm trying to keep it up there so you can see it. So half of that. So the moles of the silver chromate is equal to whatever that half of that. 0.0375 divided by 2.0188. 0.0. Well, just change it to 9 mole of Ag2CrO4. I hope everybody didn't get too confused. And then times whatever the formula weight of the silver chromate. And that'll give you your grams. But getting to the moles is in essence is the central core of the problem. So go back up here and look at it again. We'll walk through it. You got your solution data right here, but the reason I didn't go equal, just to review this, is that I don't know which one's a limiting reagent. That's why I didn't equate them. And so we calculated moles divided by the respective coefficient and found out this was smaller than that one. Checked the normalization on it. And so this one being the limiting reagent defines whatever amounts of silver chromate. And since it's a 2-to-1 reaction ratio, we're using twice as much in moles of silver nitrate as we would use in the silver carbonate, chromate. Anyway, we divide that one by 2. See, all this down here was just finding out how much chromate we use. And this is the essence. The problem is right here. This is the answer to your problem down here. So this is how many, this will produce half as many moles of the silver chromate, and so that's 0.019. Like that. So you have to go through each one and determine if there's a limiting reagent involved in this thing. Okay. It looks like it's got an answer 12.4 grams. So you can check it out. Okay, so here we have 2 sodium hydroxides and a copper sulfate. Goes to copper hydroxide and sodium sulfate. And the problem says 25 milliliters of 0.35 molar sodium hydroxide. So we have 25 milliliters of 0.35 molar in the sodium hydroxide is added to 45 milliliters of 0.125 molar in copper sulfate. How many grams of copper hydroxide is produced? So and this right here. So we want to first find out who's the limiting reagent. So we want to convert these to moles. So I have 0.025 times 0.35 mole of the sodium hydroxide, and plus whatever, separate them. And then I have 0.045 times 0.125 mole of the copper sulfate here. And so 0.025 times 0.35 gives us 00875. Moles here is the sodium hydroxide, and the other one is 0.045 times 0.125 equals 0.00563 mole of the copper sulfate right here. So we want to divide these by respective coefficients and see who's the smaller number, and then work back from the limiting reagent. So that one will give us 0.00563 for that number, and 0.00875 divided by 2 is 0.004438. Okay, that's, of course, this is the smaller of the two numbers, so this is the limiting reagent right here. And again, we have to go back to 00875 moles sodium of the sodium hydroxide to work the problem, because we're looking for this one. This one's going to be in excess because it's not the limiting reagent. Limiting reagent goes away first. It's the compound which, when consumed, reaction stops. So everything else is left in excess. Okay, so we want to work our problem from 00875. Well, that's a 2-to-1 reaction ratio. So if we're using 0.00875 mole of sodium hydroxide, the yield is going to be half of that. That's what the equation says. So the moles of copper hydroxide is equal to 1/2 the moles of the sodium hydroxide. Am I still with me on that? Okay, so we have 1/2 of 0.00875 mole of the copper hydroxide yield. Bring that up here. So we should use 0.00438 mole of the copper hydroxide formed, and then times the formula weight of the copper hydroxide. Of course, will give you the grams of copper hydroxide. So once you get to the moles, everybody should be able to handle it from there. Looking at what volume of 0.9496 molar HCl is required to neutralize 20 milliliters of 0.809 molar sodium hydroxide. So in this problem, say we have a burette, and out in the burette says what volume of the 0.496 molar HCl is used to neutralize 20 milliliters of 0.809 molar sodium hydroxide. So what you're doing is you've got your two reactants separated. One is in the burette and the other one is in the beaker. And so you have, say, an HCl plus NaOH reaction. Went to NaCl plus, of course, H2O. Okay, so it's a real simple molarity times volume, molarity times volume, because you're not being asked to determine an outcome of this based on mixing two solutions. So you don't have to figure or calculate or determine a limiting reagent here. So you can say moles equals moles. Moles HCl react moles of sodium hydroxide, and then go molarity times volume of the HCl, the acid, is equal to molarity times volume of the base. And so our volume of the HCl is our objective, and it's 0.496 molar, and we're adding that into 20 milliliters of 0.809 molar. Now, we can leave it in milliliters because both sides have the same units. If one side was grams or moles, then we'd have to work out of liters. So understand that. So our volume of HCl in this one is 20, 0.809, and molarities cancel out, 0.496, and it all comes out in milliliters. I get 32.6 mils. And so you're going to have to do a pre-calculation to determine how much you're going to have to add. You just don't want to start dumping it in there, because when you get close to what we call the equivalence point, the neutralization point, the reaction goes very quickly through the equivalence point, and this will make more sense later when I show you a titration curve and how it, as you get closer to the neutralization, pH changes very, very rapidly in neutralization. So this calculation is going to be very important to you as we go into, especially into lab work and titrations. Okay, so we have a magnesium nitrate, and it's aqueous, plus a couple of potassium hydroxides, going to 2 potassium nitrates and magnesium hydroxides. So that's going to come out as a precipitant driving force in the reaction. Now this one we have to deal with the limiting reagent again, okay? Because it's just mixing two solutions together. When they do in that context, you don't know which one's dominating the reaction or controlling the reaction. 25 milliliters of 0.235 molar is reacting with 30 milliliters, or mixed with 30 milliliters, 0.26 on this one. And really we're looking for how many grams are precipitating over here. But we first have to find out which one of the reagents controls the reaction. That'd be the limiting reagent. So limiting moles of each one, 0.025, 0.235 a mole. And this one is 0.03 times 0.26 mole of the potassium hydroxide. And so that's 0.0059 mole of the magnesium nitrate and 0078 mole over here. So we're going to divide that one by 2, that one by 1, 0039. So there's your limiting reagent right here. So we divide by the respective coefficient. The smaller of the two numbers is your limiting reagent. So the yield depends on the potassium hydroxide. Well, that's 2 to 1. So if we're using, we don't need it anymore, you go back up here. So you use 0.0078, will give 1/2 of that, 0.0078 mole of the magnesium hydroxide. Running out of space here. And so what's that, 0.0039 mole of magnesium hydroxide yield, and then times the formula weight of the magnesium hydroxide gives you grams of precipitate. You figure the formula weight is adding up to the atomic weight. So hopefully the work we're doing here is starting to make some sense a little bit. 60 milliliters of 0.322 molar of potassium iodide are combined with 20 milliliters of 0.530 molar lead nitrate. How many grams of lead iodide will precipitate? Well, we have 2 Ki plus lead nitrate goes to 2 KNO3s plus PbI2. And they want to know how many grams of that if we mix 60 milliliters of the potassium iodide and 20 mils of lead nitrate. And so converting each one to moles divided by the respective coefficients. Zero 0.019 molar here, mole, here, 0.02 times 0.53, that's a 0.0106 mole. And this was divided by 2, that was divided by 1, 0.95, and this is 0.0106. So there's your limiting reagent, and we have to work from the 019. So limiting reagents to define the lead iodide. So we don't need these anymore, but it's 2 to 1 again. So if I have 0.019 mole of potassium iodide, I'm going to get 1/2 of the 0.019 mole of PbI2. Of course, 0.0095 mole PbI2 times the formula weight of PbI2 gives you grams of PbI2. So I tried to work enough of these things to get it on the board. Sorry.